What was a basenet? A basenet was something that we represented with a directed acyclic graph, one node per random variable. Then each node, aside from being in the graph, had a conditional probability table, or CPT. And what you store in that is the conditional distribution for that particular node given its parents. So it's many distributions, one for each possible instantiation of the parent variables. So if you have k parent variables, there will be 2 to the k times the number of entries for x, so 2 times 2 to the k entries in this table. Implicitly, by having all these CPTs, you encode a joint distribution. The way we define the joint distribution is as the product of the local distributions. So the joint is, by definition, the product of the local distributions. So whenever you're given a basenet, it's a graph and a set of CPTs. Together, they define a joint distribution. The reason you specify the basenet rather than the joint distribution is because it's much more compact. But there's always a joint distribution associated with your basenet. Here's an example, the alarm network basenet, 5 random variables. The CPTs are given. And then if you want to compute a particular entry in your full joint distribution, you just grab the corresponding entries in each of the conditional probability tables. So these are the corresponding entries. Grab the numbers according to that, multiply them together. That's the entry of your joint distribution. OK, what did we assume when we started to work with basenets? We said there will be a penalty we pay for wanting to be more computationally efficient, more compact in representation, rather than working with full joint distributions. Full joint distributions, all of them satisfy this property over here. This is the chain rule. And you can apply it in n factorial different ways for n random variables. It's always true. When you go to the basenet representation, what you do is you draw your directed acyclic graph. You pick an ordering that's consistent with your directed acyclic graph. And then for that ordering, apply the chain rule. And then apply this simplification over here. What is that simplification? It's just saying that rather than conditioning on all preceding variables, you condition on just the parent variables. So after we did that, we said, by doing so, we introduce conditional independencies. The first set of them are these here. A second set of them are the ones that are implicitly introduced, not by just this equation, but by the structure of the graph. It will also imply other conditional independencies. We said you can do algebra to extract these. It's very laborious. You probably don't want to do it. So we said let's do it once for just triples. And once we've done it for triples, we can generalize to all sets of variables. So we said let's have this new thing called d-separation. And we'll say that if x and y are d-separated given z, then x and y are conditionally independent given z. This is a if-then. How did we check for d-separation? By checking, we have d-separation if and only if there are no active paths between the two variables. What does it mean to have an active path? It means that all triples along the path are active. And this was our summary of active triples versus inactive triples. OK, so that meant we could just read off from the graph whether two variables are conditionally independent given another variable for all distributions associated potentially with that graph. Yes? What was? OK, the notation is that if we shade a node in the graph, it means it's observed. It's an evidence variable. If it's kept transparent, it's an unobserved variable. So this one here is observed. This one's observed. Now, we know now how to look at the graph, and from the graph, infer conditional independencies that are guaranteed to be true, no matter what numbers you put in the conditional probability tables. That's the one big thing to keep in mind. Whenever we apply this d-separation, this condition here, what we're saying is that no matter what numbers you put in the conditional probability tables, if you then build the joint distribution, you will see that this conditional independence is true. So it's something you infer from the structure of the graph for all distributions compatible with that particular graph. Now, you could say, well, given that we can infer these properties for a given graph, one thing we could do is we could say, let's infer all conditional independencies that are implied by the graph and just tabulate them. And that gives us a set of properties that is true for all distributions that we can associate with that particular graph. What do I mean with that? We're going to compute all the independences. Let's do it. Start with this one here. What are all the independences? Let's see. Not too many, actually. We have x independent of z given y. And that's actually it for this one. That's a set of all independences. How about this one over here? X independent of z given y. Same thing. That's the only independence that we can infer from the graph here. How about this one? We have x independent of z. Anything else? No, that's it. This one here. Nothing. There are no conditional independencies that we can read off from the graph. You could do this for all graphs that you can design over triples. Yes? Okay, what I just did in my mind is I looked. Let's do a little mind reading and reannotate. So I said, let's look at this graph here. I want to find all possible independencies. What are all the possible independencies that we could find implied by just a structure? That means that there needs to be d-separation for this to be true. I need to somehow find pairs of variables such that they are d-separated, maybe given some particular evidence. And no neighboring variables can never be d-separated. So x and y and z, we cannot get d-separation because they're next to each other. So all that we have left here is x and z as a potential candidate for d-separation. So we say maybe we have some independence of x and z. And then we need to figure out if we need to condition on something or not for this independence to be true. This is a common cause triple. For independence to be true, we need to condition on y. So we'll condition on y, and that's a conditional independence we're able to extract. That's all of them, because that's the only pair of variables for which we have a path longer than 2. Same thing over here. Then over here, again, same thing. Only x and z could together participate in a conditional independence that we can read off from the graph. Let's see if there is one. I go back to my list of triples. I know that this one is inactive when y is unobserved, so I stick to this format, nothing to be conditioned on. The last one here. All variables have a direct connection, which means that we can never make a path inactive between any pair of these variables, so it's going to be the empty set here. So that's, yes?
So do I understand that we have to look back at the graph that you have of active and inactive ones?
This is your legend, yes.
Okay.
You're going to be looking back at this and using that to infer the d-separation pairs, given some evidence, and then d-separation implies independence. At some point, you'll be so used to these that you wouldn't have to look back at them, but that'll be, I guess, after Monday midnight. You'll be sufficiently used to them. Any other questions about this? All right, so in principle, we can do this. And what we can then do is we can start looking at all distributions over 3 variables, x, y, and z, and start mapping them out. We can say what we saw happen is that there were 3 directed acyclic graphs that led to the same conditional independence set right there. Then there are 6 others that end up leading to the empty set. Then there is this one here that leads to the entire set of assumptions that you could potentially have where everything is disconnected. You have all types of independencies between the 3 variables that you can imagine. And there are more. So the way you build this up is you say, what else is there? We had on the previous slide, x independent of z, but not independent of z given y. That would be x, y, z. Are there other structures with the same set of conditional independencies? No. To know that, you'd have to go through all structures and find out that none of them land with the same conditional independence set. And then you could say, well, where are these living? Let's look at this map here. The outer contour here is denoting all distributions over 3 variables x, y, z. Why is that? Well, it corresponds to distributions that can be represented by base nets that make no conditional independence assumptions. If you make no assumptions, that means you can represent any distribution. Then the extreme of making the most assumptions is over here, is the smallest set here, and every point in here pictorially represents a distribution that has all these independencies to be true. And then you have some sets in between, like this one over here, for which this one assumption is true, and that's it. And that's a medium-sized set of distributions. So what we're looking at here is we represent a distribution as a point in this little cartoon picture, and we show the sets of inclusion of, for example, distributions that satisfy this set of assumptions will also satisfy this set of assumptions, because that's an empty set of assumptions. And so you have an inclusion where some distributions can only be represented by this type of structure over here, but then some distributions can be represented by more specialized structures here and here, depending on what kind of assumptions these distributions make. So the important high-level thing here is that when you see a base net, you shouldn't think yet, if you just see the graph, you shouldn't think yet of a one distribution kind of thing, but you should think of it as representing a whole family of distributions. And the distributions that can be represented are distributions that satisfy certain conditional independence assumptions. And what we saw here is that sometimes that structure you're looking at is not the only structure that can represent the same set of conditional independence assumptions. What that also means is that at the distributional level, you cannot really distinguish between these 3 structures. They represent the same family of distributions. You might prefer one over the other because it's easier for you to draw one and to come up with the conditional probability tables associated with one structure than with another one. But mathematically, they're equally powerful in terms of expressing a joint distribution. So whenever we give you a distribution, we say, what's the corresponding base net structure? If it's one that falls into this category, all these 3 choices are essentially equally good if you're given the joint distribution. You can't distinguish between these 3 just by looking at the joint distribution. If we give you a story and we say, well, this is what the conditional of x given y looks like, well, then naturally you want something where you have x given y explicitly appear, because then it'll be easier to fill in that conditional probability table. Any questions about this? Over there. Yeah, what is the cost of adding arcs? Why not add all the arcs? Then your base net will always be able to represent the distribution that you care about, no matter what the distribution is. That's correct. The cost of adding arcs is that how expensive it is to represent a conditional probability table is 2 times 2 to the k entries for binary variables. In general, it would be d times d to the k, where k is the number of parents, d is the domain size. And so if you want your representation to be compact, you want a small number of parents. There was another question somewhere. Yes?
Why don't we have one where an arrow points from x to y and an arrow points from z to y?
X to y and z to y. That's right here. That's another, not all of them are shown, so that's another one here. And where would that one lie? Let's draw it in the map here. Where would that go? The green region in the middle makes all assumptions. So all those will be in the set, in this set S4, let's say. How about the red region? That's a different assumption it's making. It's assuming that x is independent of z given y. So the red ones are not compatible with the ones in S4 necessarily. And then, of course, all of these are compatible. So you'd have some set that would have all of this, nothing in the red, and maybe some stuff over here. I mean, it's arbitrary where I draw these marked regions within a certain color, but it is true that everything within the green will be also inside S4, and some section of this outer cyan colored thing will be part of S4. And nothing of the red that's not also in green will be part of S4. Any other questions? Yes?
So you said you can make any of the representations using the ones below. What does the only third joint distribution, what it means?
Say that again?
What does that first bullet point mean?
What it means is that, let's say you had a structure like this. X, Y, and Z are disconnected. Then every distribution that you encode with this structure will have the format Px times Py times Pz. That's a very limited version of this type of distribution that you can represent. You can come up with distributions that you cannot represent this way. Because this is saying for all x, y, z, P, x, y, z has to be equal to the product of the individual ones. And that's a very strong assumption, and that assumption is implied by this particular structure. If that assumption is not true, you don't belong in that family of distributions that can be represented with this graph structure. So that's why you're limited, because of the assumptions you make. Yes, if you draw this graph over here, you make all of these assumptions. If you draw any of these graphs, you make just this assumption. Any other questions about this? Yes? That's absolutely correct. So just to rephrase that so everybody can hear it clearly, the subset of distributions you're able to encode with the green set of assumptions is a subset of the set of distributions that you're able to encode with the red set of assumptions, which in turn is a subset of the distributions you can encode with the empty set of assumptions, the blue. Any other questions about this? Okay, then that wraps it up for representation. So the recap is basenets are a way to compactly encode joint distributions. There are guaranteed independencies for these distributions that you can read off by just looking at the graph without doing any math. The way you read it off is by using d-separation, which is a graph-based algorithm. It doesn't look at the conditional probability tables. The one thing we've emphasized several times last time is that the independencies you read off from d-separation are just the ones that are guaranteed to be true no matter what numbers you put into the conditional probability tables. That being said, for a particular set of entries in the conditional probability tables, even for a very complicated graph, you could still have more independencies. And the kind of typical example for that is, even for the fully connected graph, you could put in there every entry of the CPTs is 0.5, which means all independencies are true. But you couldn't read any off from the graph because you fully connected everything. So it's just something to keep in mind. And that's why we always go in one direction. We always say, what is guaranteed from looking at the graph in terms of independencies? We'll never ask you what is guaranteed in terms of dependencies. Or if we do, then you should say nothing is guaranteed in terms of dependencies. All right, that's representation. Let's look at inference now. We'll see a couple of inference algorithms. We'll today look at enumeration and variable elimination. Next time we'll see its NP-complete and why we might want to use sampling to do approximate inference instead of exact inference. All right, what's inference? You start out with a set of conditional probability tables, and somebody asks you the answer to a probabilistic inference query. For example, what is the posterior probability of some query variables Q, the distribution for Q, given some evidence? Typically, this conditional probability table is not one of the ones given with your basenet. It will be something about variables that are not already parents and its child. So what do you do to find that? Another question one might ask is, given these evidence variables, what is the most likely configuration of all the other variables that I haven't seen yet? These are the two most common queries. We'll mostly focus on this one, but the techniques we use generalize fairly straightforwardly to this type of query here. And when we look at speech recognition, we'll cast it into this format here. All right. So inference by enumeration is something we can always do. It's kind of our fallback inference method. Here's the recipe. You state the marginal probabilities you need. You figure out all atomic probabilities you need, calculate and combine them. All right. Example, probability of plus b given plus j plus m. What do we need? We need this one on the top, this one at the bottom. How do we compute those? Well, how do you get the marginal over 3 variables? You compute the full joint, and you sum out the variables that don't participate in this marginal over 3 variables. So you compute the full joint entries, sum out over the hidden variables, which in this case are, let's see, what are we summing over? Plus b plus j plus m. We have m, j, b in the query. So this is hidden 1. This is hidden 2. We sum out over the hidden variables and get the answer to the first part of the computation. It's not great because you're blowing up things. You're building these joint probability table entries, but it works if you have the time to wait for it. You can do the same thing for the bottom one. Make the division, and that's your answer. What if your BaseNet looks like this? You run inference by enumeration. Well, how expensive will that be? You end up summing over all hidden variables. So what will happen is you do something, you have some query. There will be some number of hidden variables, and then the number of terms in your inference will be 2 to the number of hidden variables. That can be very expensive. Typically, your query will be about a small number of variables. Most of the variables will be hidden, and you do a lot of work. So why is this slow? Essentially, what you do is you build the entire joint distribution. You unpack these conditional probability tables into a join of all of them, get the full joint, and then you squeeze out the information you really care about. What we'd much rather do is not blow things up and then squeeze the right thing out. We'd rather just blow it up a little bit, squeeze out what we need, blow it up again, squeeze out again, and keep going that way. So that's the difference between variable elimination and inference by enumeration. The fact that in variable elimination, what we're going to do is we're going to, yes, join things together, but once we join something together, we're right away going to squeeze out everything that doesn't matter and then move on. This picture here is a pretty good summary of the remainder of the lecture. If that picture makes sense in math equations to you, you're all set. All right, so we'll introduce some notation so you know what all these things mean that we're looking at in these pictures. So we'll look at something called a factor zoo. What does that mean? We're going to look at all kinds of distributions and tables that aren't even distributions, and just make sure that we understand what they are. Because we'll need them. Once we know what they are, we'll just use them in very simple ways, and everything will work out. Joint distribution. Remember what that is? It's a join between 2 variables or more variables. All the entries sum to 1. Here's an example. If you want to keep track of the match between the cartoons and the distributions and general factors that we look at, a joint distribution is represented by something with only heads. Because if you look at a conditional, let's say x given y, this is the head, this is the tail. A joint distribution only has head variables, so this is our picture for a joint distribution. A selected joint, what does that mean? That means that from the joint distribution, you select a subset of entries. So you fix for one of the variables what it is. In this case, x is fixed because x is lowercase, so it's not a variable, it's fixed. Here's an example. We fixed cold, temperature to be cold. That's what we get. All right. The number of capitals, something to keep in mind, is the dimensionality of the table. This here is a 2-dimensional table. This here is a 1-dimensional table because only one variable is varying over here. 2 variables are varying over here. Yes?
For the bottom table, would you normalize it?
Good question. So that's a really important observation. We don't normalize things here. We keep things as is. So a lot of these factors will not sum to 1. Here it actually sums to something meaningful. It sums to the probability of cold. There will be other factors where it doesn't sum to anything meaningful at all, and we'll just be fine with that. Okay, how about this one, a conditional? A single conditional, y is the variable, capitalized, x is not a variable, it's held fixed. What will this sum to? It will happen to sum to 1 because it's a distribution for y given a fixed value of x. Here's an example. Cold is fixed, and weather, well, temperature is fixed to be cold, weather can vary. Here's another one. You can have a family of conditionals. What that means is that you have something of this type over here. Now it's x given y. You have x given small y for all values of y. So this now is a two-dimensional table because both w and t are varying, and that's what it looks like. You have two distributions stacked into one table. Here's a specified family. This is kind of the weird one. What happens here is this is not a distribution in the sense that we've been looking at before. It's not even a distribution in any other sense. It's just saying I'm going to fix the head and let the tail vary. You can do that. Nothing that stops you from doing that. Building a table that lets x vary and y is fixed. In this case, rain is fixed. Temperature is the variable. So we have variation here. This one's fixed. Why would you do this? We don't know yet, but definitely you should be able to do this. If I give you a joint distribution, build a specified family table. All right. So our summary is that there's many factors there. No matter what they are, they always look of this format, but some of them could be lowercase, meaning they have been instantiated and are fixed. They're always tables. The dimensionality of the table is the number of variables that is kept capitalized. Meanings, sometimes meaningful, sometimes not. Okay, now that we're happy to work with factors, let's start using them. Here is a BaseNet that will be our running example for variable elimination. Rain could cause traffic, could cause being late for class. So here's the full BaseNet with conditional probability tables. How do we run variable elimination on this BaseNet? We'll track some objects that we call factors. And the initial factors are the conditional probability tables. So initially, we just start with these. If our query involves evidence, then we will narrow it down to the entries in these tables that are consistent with the evidence. So if we had evidence of plus L, then we would look where L appears. L only appears over here. So for that table, we'd narrow it down to where L is positive. And we'd end up with this set of factors as our starting point. For now, what we're looking at is very mechanical. I'm just describing a procedure. I'm not deriving it. I'm just saying, if we do variable elimination, this is what we start with. OK. Then what we're going to do is we're going to alternate joining factors and eliminating variables. What does it mean to join a factor? It means you take two factors and essentially perform the database join. What that means is you take the product set of the original sets of the variables and then build a full table over that. Let's look at an example. If you had PR and PT given R, what are all the variables here? You have R and T. That's it. So your table would be something with R and T. R and T are both capitals here. They're both variables, so we need all possible combinations. And then the entry we fill in here is just the product of the corresponding entries. So the first one, plus R plus T, is this one here and this one here. 0.8 times 0.1, which is 0.08. That's the first entry. We do that for all four of them. That gives us the factor that's the join of the two original factors. So this is what we get. Now we know how to join factors. Great. The way we denote this in the BaseNet is that now we have these two variables appear together in one node because we join them together. It's like a super variable containing both of them. Okay, we can repeat this. So you could join these two together, get a new factor. Then you could grab another factor in your BaseNet and join it with this one, and then you get something three-dimensional. So let's do that. We already joined on R in the previous slide. We got this result over here. Now let's also join on, let's see, maybe we'll join on T, which means we have to combine. Hold on, let me recap just what we did. What we did so far is we started from a BaseNet. We picked a variable R. We said, let's join on that variable. What does that mean? It means you pick all tables that have that variable, compute the join. This table just transferred over. These tables had the variable R, so they were joined. Gives us a new structure of the BaseNet. At this point, we can again pick a variable to join on. Let's say we join on T. That means we pick all factors that we currently are working with that have T in them. That's all two of them. Now we join on those two. We join those two to get a table over R, T, and L. What does it look like? Just build up by multiplying together the corresponding entries in each of these tables. Okay, that was join on R, join on T. We have the full joint. That's fine. Now we marginalize. What do we do to marginalize? We sum out the variables we don't care about. This is a projection operation. You get rid of some variables, makes things smaller. If we just start with this table here, we want to marginalize to just get a table over T. It means you sum over R. What does that mean? You get PT, and you have an entry for plus T, negative T. For plus T, what do? You sum corresponding entries together. Plus T, that's 0.17. This one, negative T, is these two entries, so 0.83. That's what it means to marginalize over, in this case, the variable R. These are our two basic base operations that we'll be using, join and summing out. Summing out is the same as marginalization. Okay, let's look at this again. We have this full join that we computed after joining on R, joining on T. Then we could sum out R, means build a new table where R is gone, but still all combinations of T and L. And you compute it by summing together the corresponding entries. For example, this entry here comes from plus T plus L, which would be this one here and this one here, summed together. Then we sum out T, get a table over just L, and what we found with this computation is the distribution for L. Remember, our original BaseNet looked like this, R, T, L. What did we have? We had P for R, P for T given R, and P for L given T. So we did not have available the distribution for just L. This operation, join, join, eliminate, eliminate, gave us now the distribution for L. So we just did inference for the following query right here. We just computed the answer to the inference query. What is P of L? Yes?
How did you choose which operation to do? Just go?
We'll get to that. It's important to choose that in a clever way, but mechanically you can always pick any ordering you want. The only constraint that you have is that you cannot sum out a variable before you have joined on the variable, because then it would be living in multiple tables, and you can't properly sum out a variable that's still in multiple tables, because then you would lose the connection between these tables. Okay, so we did join, join, eliminate, eliminate. That was our procedure. We could switch that around. We could do join, eliminate, join, eliminate. If we did that, it would be called variable elimination. So the ordering in which you do the operations of joins and elimination, if you pick a variable to join on, then eliminate that variable, pick a variable to join on, eliminate that variable, and so forth, you're doing variable elimination. So this is what variable elimination would look like. You still join on R. Now rather than next joining on T, you say, well, we have joined on R, that means we can eliminate R. So let's just do it. Eliminate R gives us this. And what happens here is that this table here became smaller early on, and what ends up happening is we work with smaller tables overall. Now we can join on T. After we join on T, we can sum out T, we get our final result. So we never build the big table by running variable elimination because we can eliminate early and make tables smaller as we go along. Okay, what we haven't looked at yet is what happens if there is evidence in the query. What we did so far was answer the query, what is P of L? But there was no evidence. So let's repeat this procedure with evidence. These are our initial factors. We're interested in the condition of L given plus R. That means the factors become smaller, made consistent with plus R. After we have done that, we go through the same procedure as we did before. So we say, okay, we'll eliminate all the variables other than the query variables and the evidence variables. Why don't we eliminate the query variables? Well, we need them because it's a part of our answer. We can't just get rid of them. Evidence variables, well, you can't really eliminate them. They're already instantiated. They're fixed. You can't sum out over them. You keep them whatever they're instantiated as. Okay, so if we did that, we'd end up with something that looks like this. It would be unnormalized. We would find the joint of the evidence variables and the query variable. We want the conditional. All we have to do if we have a joint and we want the conditional is to renormalize, and that's what we do. We renormalize, and we get the conditional of L given plus R. So that's a complete procedure for variable elimination. Here's the general version. You're given a query, some query variables Q, some evidence variables E1 through EK. You have some initial factors, which are all the conditional probability tables in your BaseNet. You instantiate the evidence variables in those CPTs, so that already shrinks them down a little bit. Then you go through a loop. While there are still hidden variables. What does that mean? Variables that are not query variables or evidence variables, all the other ones. You pick one, and as you pointed out, it's going to be important in which order you pick them, but for now, let's assume you just pick one. You join on that variable. What does that mean? You take all factors that have that variable in it, join them together. Once you've done that, you're allowed to sum it out, which makes this factor a little smaller, and you repeat. Once you're done with that procedure, you might still have many factors left. That's possible. These factors will only have evidence variables and query variables in them. At that point, you join all the remaining factors together. The result here is P, Q, comma, E1, E2 through EK. You normalize. Once you normalize, you get out the answer to the query, which is Q given E1 through EK. What's the question there? Join means what we've been looking at in the examples here. So an example join is given over, let's see. We did a join over here. We said, let's join these two tables. It means you build a new table that has all the variables in the original tables. And the way you compute the entries in the new table is by looking at the corresponding entries in the original tables and multiplying them together. This can be happening for two tables, but you could have 5 tables that are joined together. You end up with a bigger new table typically. And again, you follow the same procedure. Line by line, you check what are the consistent entries in the original tables, multiply them together. That gives you the new entry in the new table. No, it doesn't, because the multiplication is commutative, so the numbers can be swapped left, right. Yes?
When you do a join for all variables mentioning for all values mentioning h, is that join of h with the parent?
So the question is, what do you happen to bring together when you do the join? And it depends on your basenet. So if you are very lucky, so to say, if you join on a variable h, and that variable has no children, only has parents, then that would be the only table that participates, and your join would be an empty operation. Nothing would happen because it's the only table. But if your variable is not only a child, but at the same time also a parent of many other variables, then for each of these other variables there will be a table. So if you are the parent of 5 variables, and you're the child of some other variables, you would join together 6 tables total. 1 for each of the children of your variable, and then 1 for the variable's own table. That would be initially. After a while, what you do is you don't look at the basenet anymore, but you just look at the factors you're currently working with. We'll see a couple more examples. Any other questions? Yes? Which slide? Evidence 2. Forward. All right. So evidence 2. Okay, these numbers came from a computation that we didn't explicitly do. So if you were to run variable elimination for this query here, what you would do is you would join on all hidden variables. The hidden variable here is t, is the only hidden variable. So you would join these together, which would give you a new table, which would give you a table over p, t, plus r, and l. So you'd have, see if we can draw it here, r would always be plus r. You'd have l and t. We'd have plus l, minus l, minus l, plus t, plus t, minus t. And the numbers here would come from the product. We'd have 0.3 and 0.8, give 0.24 for the all positives, so 0.24 over here. Then 0.7 times plus t minus l, that's again here, plus t minus l. That's 0.8 times 0.7, so 0.56. Then minus l plus t is over here, and did I do something funny? This is not right. Plus l minus t is here, 0.2, plus l minus t is here, 0.1. So this would be 0.02. Plus t minus l plus t is this one, minus l plus t is this one here. So that would be our 0.56. And then the last one, minus l minus t, that's here and here. So that's 0.18. That would be our join on t. After our join on t, we have this factor left and this one here. After joining on t, we would sum out over t because we don't want t. So sum over t would give us a table with r and l, plus r plus r. L could be plus l or negative l. The sum over t for plus l is here. So the top one would be 0.26. The bottom one would be minus l plus r is here. Would be the sum of those, which is 0.74. This now is our factor p l comma plus r. Then we would have this one here and this one here. So 2 factors left, no hidden variables left. So we're at the end of the while loop. We would join together all factors that remain, means joining these two together, which would give us a new table over R and L plus R plus L plus R plus L, which is multiply everything with 0.1, so we end up with 0.026 and 0.074. That's the distribution for plus R comma L. This one was actually this meaning here, L given plus R. Now we renormalize this one, and we have the answer to the original query, which is L given plus R. So that's the complete computation. Wasn't shown. We just jumped right to this thing here and showed the normalization. Any other questions about this? Okay, let's take a break here then and see a couple more examples and the more general kind of derivation after the break. This is the procedure we're going to work with for the remainder of lecture. And what we're going to do is we're going to look at the same procedure in a couple of different ways. So for now, the way we've looked at it is we've looked at it as we have a set of tables. We join, we eliminate, we join, we eliminate. That's the procedure. When we think of these tables being joined and then variables being eliminated, we've made it pretty concrete. We've said there is these tables. We actually join them together. We look at the numbers. We eliminate, and so forth. Now we're going to take it at one level up and not write out the tables anymore. Okay? So here is a new inference problem. We're going to follow the same procedure but be less explicit about the entries in the table. Just to think about what happens when you run variable elimination. We have this query over here, the conditional of B given J comma M. These are our initial factors, 5 of them, because there are 5 conditional probability tables, 5 variables. And we instantiate the evidence that we have observed, J and M. For each of these, there are associated tables, but we're just not going to draw them now. Then we choose a variable, let's say A. We need to pick one of the hidden variables. So we need to pick, what are the hidden variables here? Hidden are A and E. So you could pick either A or E. Either way, you're doing the right thing. Doesn't matter, but we're going to pick A here. Either way, it will be variable elimination. That means you have to grab all the factors that have A in them. You join those. What do you get? You get a table over all the variables that were already in here. So you get a table that contains J, M, A, B, and E, all of them. If you're worried about which variables appear behind and which one appear in front of the conditioning bar, the highest order bit is don't worry about it. We don't need to know. You could just as well write something called, I have a factor F over J, M, A, B, E. Because we never use that information. We'll never use the information, so if you want to keep track of it, think it through. Good for you. That's fine. If you say, I don't want to keep track of it, equally good, the algorithm will work just as well if you call this a factor that has 5 variables, 2 are instantiated, 3 are variables still. After we join, we sum out over A, which is the one we chose to join over. So sum out over A, and we get a new factor. Again, this factor, we could call this one F prime, and this one F, J, M, B, E. Perfectly fine. Questions? Yes? Okay. The hidden variables are the ones that are not query variables and not evidence variables. So you look at all the variables, all 5 of them, and you check which one is a query variable. B is the query variable, so it's not a hidden variable. J and M are evidence variables. They're given. So this is an evidence variable. M is an evidence variable. We're left with A and E. Yes?
So what factors are that?
Sorry, say it again?
What factors do you have that factor there?
Okay, what factors remain? These factors have been used. They're gone. We don't have them anymore. Instead, we now have this one. Now, which do these correspond to? This is M given A, J given A, and A given B comma E. Because we joined on A, everyone that contains A has been used and put into a new factor altogether. So we're left with this, this, and this. Yes, this summation here is a sum over all values A can take on. Correct. All right, so that's our intermediate result. We went from 5 factors to 3. There's only one hidden variable left, E. We join on that hidden variable. That means grab all the tables that have E in it, this one here, this one here. Join them together. This gives you a new table over all variables that are in the original factors that you are joining together. Then you sum over E, which is your variable that you joined over, and you get a new factor which contains the same variables except for E, which is sitting here but not sitting here anymore. Again, you could call this just a factor. You could call this my second factor, F2 prime over J, M, E, and B. And this would be F2 over J, M, and B. Remember, it matters which ones you capitalize, which ones you don't capitalize. Capitalized ones are the variables. The ones you didn't capitalize are the ones that are evidence variables. They're instantiated. All right. We have 2 factors left. Yes? Which middle equation? OK. The way you know what variables participate is you just write down, I'm going to do it with F. You write down F2 prime. You wonder which variables participate. You just look over here. You have E, you have J, you have M, and you have B, just by transferring them over. How do you get the form that this is conditioned on B? It doesn't matter, but if you want to figure it out, you can reason about these things you compute, and you can actually, I believe, but I don't want to 100% confirm this, I believe as long as you only appeared behind the conditioning bar, you will remain behind the conditioning bar, and once you appear ever in front of the conditioning bar, you will appear in front. They're just tables. Just some table. This is just a table with E and B vary. And so if they're binary, there is 4 entries in the table. This is just a table. E and B vary. So if they're binary, that means 4 total entries, 4 numbers corresponding to that. That's all they are. They're the same. It's just a different way of writing the same thing. One way of writing is you try to keep track of which is in front and behind the conditioning bar. The other way to write it, you say, I'm not going to bother. That's the difference. All right, so we know how to do this. Then we have 2 factors left, no hidden variables left. So we're at the end of the while loop. We say, let's join everything together. Compute the join. Again, if you wanted to not keep track of what this is, you could just write F3 of JMB, equally good. You do know when you're done, though. No matter whether you keep track of things or not, you're guaranteed that when you are done with your variable elimination, at the very end, what you end up with is this thing over here. It will always be that. Nothing will be behind the conditioning bar. Everything that's still remaining will be just sitting there. Guaranteed. That means it's not normalized yet, so we're going to normalize to get the conditional for B given J, M. Again, normalization just means you sum all the entries in the table and then divide everything by that sum. So this is the same thing we've seen in earlier examples now, just by looking at the factors that we generate, not by putting the tables out there, but just keeping track of which variables participate in which factor. Any questions about this way of representing things? At the end, you have to join on all the remaining variables. You have no choice. Everything needs to be joined together. I mean, technically, there's an exception. If you had a basenet that really consisted of 2 basenets, and you didn't realize that, and you didn't just run inference in the basenet that where the query variables were, right, then it's a little, you could, in principle, just throw out the other basenet. If there are no query, no evidence variables in the other basenet, you can just throw it out. But the general case is you would just multiply everything together and then do a normalization. Could be more than one variable. You could be joining on 10 variables at the end. Yes? What is the? Next slide, or next. Okay, so next slide actually. Here we go. What is the mathematical explanation for doing this procedure? Like, why is it okay to join, eliminate, join, eliminate, join, eliminate? Why is that right? Right? Mechanically, we've just said, here's a procedure. It seems right, but we haven't proven or really explained why it gives us the right result. Here's the same example we just looked at. Work through, not just mechanically what the algorithm does, but work through in math. What are we interested in? In the conditional of B given J and M. We know that computing conditionals is equivalent to computing the joint between B, J, and M, and at the end we'll normalize to take care of the fact that we computed a joint instead of a conditional. What is the joint? Well, when we're given a basenet, we're not given the joint over just B, J, and M, but what we do know we can always do is compute the full joint. So what we say is let's express this distribution or this probability here over 3 variables by using the full joint entries over all variables and then summing out the variables that are not in here. So we're saying the distribution for B, J, M is B, J, M, and E, and A, but then we sum over all possible values of E and A. That is just saying the same thing with more variables as saying Px is equal to P sum over Y, Px comma Y. That's what we're using in that first step. All right, that's always valid, no problem there. Then the next thing we do is we say, well, this joint, we could compute that. If that's what we did, that would be really inference by enumeration. We compute the joint and then do the summation over the hidden variables. That's inference by enumeration. We want to do something more efficient. So let's look at what this really is. Let's look inside this joint. It comes from a basenet. Because it comes from a basenet with this structure over here, we know that we can write it this way. This is just using the assumption that we have a basenet of this particular structure over here. It means the joint factors in this particular way. Now comes the special thing, the kind of how do we speed this up? Why is it that in variable elimination we can do this faster than doing full inference by enumeration? Remember this thing? X times y plus z is equal to xy plus xz. That's what we're using. In a more elaborate way, this is what we're using, what we're going to be using here is if you multiply together u plus v with w plus x with y plus z, that is 3 sums and 2 multiplications. That could equivalently be the left-hand side here, which has many more multiplications and many more sums. So effectively what we're going to be doing is start from something that looks like the left-hand side over here and transform it into something that looks like the right-hand side. That's our computation we're doing. That's the idea. How are we doing this? Well, okay, we have this expression over here. We're summing over E and A. How do we get this to be working a little more efficiently? We say, how about A? Let's look at A first. Where does A appear? A appears over here, over here, over here. Only in 3 of these factors. What does that mean? That means that this summation over A can be moved in here. The 3 factors over A are still in the back, but the summation over A doesn't have to wait till we've also multiplied everything else. We can sum out over A early. After we multiplied all factors with A, we can already sum over A. Okay, let's say we did that. What is this thing over here? What is that for us? That is a join over A and then a summing out over A. That is one step in variable elimination. That gives us a factor over the resulting variables, factor F1. Now let's look at the new expression we got here. We're summing over E. We know that we don't need to postpone the sum till we have multiplied everything together. We want to move that sum in as far as possible. How far in can we move it? We can move it till over here. So then we have E here, but B up front, PB up front. We can do this computation first. What is that? That's a join over E and then summing out over E. which gives us a new factor, f2 over b, j, and m. Now, at the end here, we're left with a join on b. So we just saw the same computation we looked at before, but we now derived why this is the right thing to do when you want to compute the answer to this particular query. So we see that this idea of, rather than joining everything and then eliminating everything, but into leaving it instead, is the same thing as, yes, here you were joining everything. You identify which hidden variables participate in a small number of factors. Put that small number of factors at the end of your product. Then move the summation right in front of that and do that first. If you have a lot of variables, this can save you a lot of computation. Any questions about this? This is really the proof by example that variable elimination is a correct procedure. Yes? How much better is it? Good question. We'll get to that. Any other questions? So let's see how much better this can be by looking at another example here. Actually, this example, what we want to do with this example is just to kind of show you how little we might write down when we work through this. The query is this thing over here. x3 given y1, y2, y3. The y's are the bottom variables here. X's are sitting here. The query variable is this one here. Query variable, evidence variables here. Z, x1, and x2 are hidden variables. So one way to keep track of your variable elimination procedure is just what I show here on the slides. You say, what are my initial factors? These over here. All the conditional probability tables with the evidence instantiated. Then you pick something to eliminate. We pick x1 first. What will that do? It'll introduce a new factor. Which factors participate in this new factor? All the ones that have x1 in it. So we have the factors with x1. Both sit over there. Multiply them together, sum out over x1, gives us a new factor over which variables? Z and y1. Why those two? Because those are the two that appear over here. That means factors with x1 are gone, and so we're left with this new one and the ones up here that are not crossed out. This is our current status. Two hidden variables left, x2 and z. We pick x2 next. Okay, let's eliminate x2. What does that mean? We introduce a new factor, which is the sum over x2 of the product of all factors that have x2 in it. Which one have x2? This one here, this one here. Both of these are put in here in this expression, multiplied together, summing out over x2. Gives us a new factor over all variables that are sitting here except for x2, which is z and y2. These are gone now. These are our factors left after that step. One hidden variable left, z. So we eliminate z. Multiply together all factors with z, which is this one, this one, this one, and this one. 4 of them. Multiply them together. Sum out over z. You get a new factor. The variables are, well, you have y1, y2, and x3. So those are the ones that appear over here. We're left with 2 factors now. No hidden variables anymore. That means we just join everything together. And we know that after joining things together, we are guaranteed that this is equal to the joint of y1, y2, y3, and the variable x3. Then just we renormalize, and we're done. We find the answer to the query. All right, that was our last kind of full-blown variable elimination example. Any questions about this one? Okay, then here's the big question that you have to ask yourself when you run variable elimination. Assuming you understand this procedure, you're happy with the procedure, you have a choice point. Every time you eliminate a hidden variable, you get to choose which one to eliminate next. Just like in A-star, the heuristic was a choice point. In CSPs, backtracking solvers, the variable ordering and value ordering was a choice point. In variable elimination, your choice point, your strategy, goes into picking which hidden variable next. Let's look at an example of how good and how bad it could be depending on your choice, and hence illustrating why it's important that you pick the right ordering. Let's consider this query over here, xn. given y1 through yn. So these are all evidence variables here. You can shade them to indicate that. Our query variable is xn, and z and x1 through xn minus 1 are the hidden variables. Let's have you guys take a minute or two to think about what you think would be the best variable elimination ordering and the worst variable elimination ordering for this particular query. And yeah, talk to your neighbor and see what you can figure out. Actually, let me define best or worst. What it means to be best is that the way we measure how good your ordering is, if you go through this process, let's say over here, and you generate factors along the way. Which factors did we generate? We generated F1, F2, and F3. And then F4 over here. F4 is unavoidable. That's the last one. That one will always be the same, right? Because that's just a joint of query and evidence. F1, F2, F3, we need to measure the size of what we're doing here. How much work are we doing? Because that's the real work we're doing, is computing these factors. We measure that by dimensionality. Here we have, let's see, we generate a factor with one variable really. So this is, dimensionality is 1 of what we generate. Here, dimensionality is also 1. And here, dimensionality is also 1 of the factor we generate. If we go back to an earlier example, the alarm case, we generated our first factor here. We here generated a factor which has d equal 2, two-dimensional. And then, so that's bad because it's bigger than d equal 1. Here we generated one with the dimensionality equal 1, just one variable. So the key is you count the number of variables in every factor you generate, and then you just see which ordering gives you factors with the lowest number of variables per factor. Keep in mind, evidence variables don't count because they don't introduce more entries in your tables. They're fixed. It's the variables that are still variable, the hidden variables and the query variables, those are the ones that matter. All right, let's see what you can come up with. All right, let's see what people came up with. Who has a suggestion for a good ordering of the variables? One where the factors stay small. Yes? Okay, choose the variable with the fewest number of unobserved children. So in this case, that would mean any of the x variables would be having 0 unobserved children, so they'd be winning out in your ordering, and z would be losing. So we'd have something, one ordering would be x1 and so forth, till xn minus 1, and then z. All right, I'm going to agree with that. Why is that a great ordering? Let's look at the size of factors that we generate this way. If we eliminate x1, who participates in that elimination procedure? Well, every factor has x1 in it. So we would have, in this case, p y1 given x1 and p x1 given z. These would be joined together, summed over x1, and we'd get some first factor, which would be over y1, which is fixed, and z equal to this over here. Then if we move to x2, what would be the factors then? We would have y2 given x2. We'd have x2 given z. Those are the only two with x2. We'd have a similar kind of computation. We'd have f2 over y2 comma z is this sum over product. This would go on till we reach fn minus 1 over yn minus 1 and z, which would be equal to the sum over all xn minus 1, pyn minus 1, which is fixed, given xn minus 1, which is variable, times p xn minus 1 given z. At that point, we would be left with factors f1, 2, 3, and so forth till fn minus 1, which are just over one variable each, the variable z. And we'd also be left with the factor pz. At that point, z would be next. We would join all of these n factors together that have z in them. Z is the z, n. So we have all of these. f1, y1, comma z times f2, y2, comma z, and so forth till fn minus 1, yn minus 1, comma z. Multiply with pz, which we still had from the beginning, and then multiply with xn given z. We would sum this over z. This would give us a new factor, fn over all the y values, which are fixed, and then xn. This would be a factor with just one variable. Then we'd still have p yn given capital xn. These would be our two factors left. We join them together. It would give us the join over xn and all evidence variables. And in this entire process, all the factors we generated had just one variable in them. That's as cheap as it's going to get, right? You can't generate a factor with less than one variable, really. So that's it for this particular ordering. How about a really bad ordering? Z first. What happens if you pick Z first? Look at the factors Z participates in. It is, for Z first, we have PZ, we have Px1 given Z, Px2 given Z, and so forth till Pxn given Z. Well, joining those together, summing over Z, would give us a new factor. This new factor would be over x1, x2, x3, and so forth till xn. So we generate a factor over 2 to the n, not to the n, a factor over n variables, which will have 2 to the n entries, which is really bad. The first ordering gave us at most 2 entries per factor we generate. Here is 2 to the n, much, much worse. So that's a very big difference in terms of computation. So the ordering is really important and can affect your efficiency a lot. So the largest factor will determine your computational complexity. You have, if there are, let's say, k hidden variables, you have k factorial orderings to check. It can be a lot of work to check that, but keep in mind, while you check those k factorial orderings, you don't have to do all the work. You just have to check, if I were to do this computation, which variables would together be in a factor, right? So you don't have to actually run the variable elimination to check different orderings and see for each ordering how much computation would be needed if you were to go with it. So it's a pre-computation you can do to check how much computation will need to happen if I pick this ordering. Does there always exist an ordering that only results in small factors? Sadly, the answer is no. So you could try all k factorial orderings, and you could end up finding that there is no ordering that gives you less than, let's say, k minus 2 variables in one factor or something like that, which would be pretty bad. So that's the bad news, and we'll see a proof for that next lecture. The good news is that if an ordering exists with a small number of variables in each factor, it's efficient to find it. So you can relatively efficiently find it if only small factors get generated, but you don't know ahead of time if that's going to be true. Because if there's only a small number of variables in the biggest factor, you can actually run a search procedure to search over all these orderings and quite efficiently find something pretty good. All right, next time we'll see the proof of why the best case doesn't always happen and look at approximate inference.